recap a little bit. So what we want to show is that from microcausality that we establish is implied by superluminality, by subluminality, we'll be able to derive some analytic properties of scattering amplitudes. From there, adding other ingredients like unitarity, we will get to positivity. So that's where we are heading to. So today is the first part, at least, will be microcausality. It's going to give us some analyticity regions, which are very useful to know and work with. So the idea is that you take a scattering process, 1, 2, going to 3, 4 for scalars for simplicity. And yesterday I was showing that you can write this in the following form with a version of the LSZ, which involves the commutator of two fields associated for particles 2 and 4 in this case. So I'm LSZ reducing particle 2 and 4, in 1 and 3 in the states or already reduced, and then writing the LSZ formula rather than in terms of t-order operators in terms of step function in time times the commutator. The reason is because this I know will vanish a space-like separation. I'm gonna leverage on this. And to simplify our life as much as possible, so this is a function for scalar of the Mandelstam invariance. So let's go in the simplified kinematics, where all results are much simpler to show. So let's go in the forward limit. So let's take t going to 0, and whatever flavor also simplicity, whatever flavor this scalar particle may have, also let's take elastic. Okay, so particle 2 is identical to particle 4, particle 3 is identical to particle 1. So it's a simplified setting. So in this, in particular, K2 goes to K4. So in this case, this formula becomes just e to the I. K2 is going to be the only momentum around in the story, because by momentum conservation, everything else is determined. So often I will just refer to this as K. Okay? And dot X, theta 0, 1, Jx, G dagger 0, 1. So I'm sandwiching between identical states, a commutator, and taking this Fourier transform. Yeah, I think it's best to work to establish these analytic properties. It's best to work with slightly different variables. So let's change variables to null coordinates. So let's assume this particle move in the x direction. Okay, so this direction is x. I can always, by rotational invariance, I can always put myself in this condition. So I'm gonna pick x direction and change coordinates in this way. Leave the rest, the other one unchanged. So 2 and 3 are unchanged. So in this basis, the metric is just du dv minus the orthogonal directions. In particular, it takes the following form explicitly, so it's 0, minus 1 of 0, 0, 0, minus the 2 by 2 identity here, and inverts 0, minus 2, yeah, I have a typo here. Yeah, no, I have a typo here. Because I'm working with mostly minus convention. In particular, the determinant here, you see, is negative. So All right, so remember this is 2 by 2, so the terminal this part is positive, so the terminal this is negative, so which is good. Okay, so in this basis, the forward amplitude, this one, take this convenience form, du dv e to the I kuv plus kvu integral of the 2x perpendicular of theta x0 1 jx g dagger 0 commutator 1. And I assume here this, okay, that I'm working, so all momenta is along the direction x1, so nothing shows up here in the exponential. This one can depend on the transverse direction, so I'm pulling part of the integration, so this part here is going to be my new integrand upon which I'm interested in looking at the action of this Fourier transform in these variables. Now, let's pause for a second. Let's look at this basic fact about Fourier transforms, which is important. I think everybody knows it, but since it's so crucial for the argument, so let me stress it explicitly. So let's consider one-dimensional Fourier transform. Now we are going to do a two-dimensional, but let's focus first on the one-dimensional, which of a function which has support only on half the line. Okay, so that's what this is. Therefore, this allows you to immediately define a new function of a complex variable. I'm going to call it P. So I'm standing analytically this function in the complex upper plane for Q positive, so with the positive imaginary part, through this integral formula. The reason this is possible is because Q is that because if this existed, this one is even more convergent. There's an exponential damping factor on top. So it's even more convergent than this one. Therefore, as long as I'm taking Q positive, so I'm extending the definition of this function to complex momenta in the upper plane. So for the imaginary part, okay, which I've been calling Q here, positive. Okay. So general lesson, Fourier transform of a function that supports a half line is analytic in the upper plane, or if the support was on the other half line, would be analytic in the lower plane, just by sending x to minus x. Okay. Let's come here now to this case, and let's look at the support of this integral here. Time x1 u d. Now this is a function that vanishes as space-like separation, so vanish here. But EI is in principle support in the past, here in the past like code, except that now there is a nice step function in front that kills the past. So it has support only in this quadrant, which is half a line for U, half a line for V, both in the positive region. So all these things here are support. Basically, you can add a theta U, theta V without any, just the same thing. I can multiply by a step function. And precisely in this situation twice. Okay? This immediately implies, so that's why I changed coordinates. I wanted to make this manifest. And this is why application. So you can extend your scattering amplitude as a function of k to be analytic in the upper ku plane and kv plane. So imaginary part of ku or v, both positive. So in that region, you're analytic. Is it clear? So this, if you want to express in terms of Mandelstam variable, for example, let's do an example. Let's take K, for example, particle 1 massive. So also particle 3, I'm taking to be the same. You look at what S. So it's going to give you M1 square plus M2 square plus 2 K1, K2. Now let's go. These are Lorentz invariants. Let's go in a frame where K1 is at rest. So this one is going to give me 2 and 1, K2, 0. K2, 0. If I look back, my variable here is nothing but Kv plus Ku. So this is. So there's a linear relation between Ku, Kv, and S. So this is S. So what bottom line of the story is that in the complex S plane, we just show that you're analytic here. So this region here, the upper S plane, you're analytic thanks to microcausality. Okay? You cannot have a pole here. For example. That would be inconsistent with microcausality. Let me anticipate that. Well, I'll anticipate. So when you take the momentum real, you're approaching the real line, you're gonna get your original amplitude. Okay, so when you go on the real axis, you get back the amplitude. And we will see that there's gonna be here in general, there's a branch cut here. There's gonna be another one here by cosine symmetry. We'll see that in a second. So you get the physical amplitude is gonna be here for positive S. So center of mass energy has to be positive to be a physical amplitude. So you're analytic everywhere. So you need to go to get real and above, have positive energy. And from above, because this is the region of analyticity we established, so that's the type of limit that you're taking in order to get the physical amplitude. Questions? No, this is you don't need to put, they are there. They are there. I'm just saying the support of this function is drawn here, is this, the support of this function. So this function vanish as space-like separation, so it vanish in this wedge. It vanish here, and it vanish in the past because of this step function. So the only support is inside the future light cone, this part. So this function has support where this step function has support. You don't need to write them, just you write, or if you want, let's not write them. I'm just saying that this integral is the same as this integral. So we are back in the case of the Fourier transform. Both things, the commutator vanishing as space-like separation and the step function. If the step function wasn't there, you would have also support, for example, you see at negative u and negative v simultaneously. So the step function is important. So in fact, the step function ensures causality, strictly speaking. The vanishing of the commutator establishes relativistic causality. So the step function is telling you that this support, so let's write it again. If it was just for the step function, which happens in non-relativistic quantum field theory, the support would remove this region only. Okay, but by relativistic causality, we mean more. It's not just that the past is not going to affect the future, but even space-like points are not affected. One doesn't affect the other. Also, this region is excluded. Okay, that's what the combination of the two. Okay, another important point here is here you see we took a particular sign for the Fourier transform, which was is important because it reflected here on a particular sign here, which reflects in which region you are analytic. What happens if I flip the sign here? What would happen? I'm still calculating an amplitude. Which amplitude? So this is a process 1, 2 going to 3, 4. If I flip the sign of the energy of K2 and the sign of the energy of K4. Yeah, so this would be exactly. So yeah, I will exchange particle for antiparticles. It will be 1, 4 antiparticle going to 3, 2 antiparticle. Okay. So let's consider that case now. It's the same integrand, just flipping the sign here. However, for the purpose of establishing a larger, so here we establish this regional analyticity. We are going to establish a larger region now, which is going to be below. So we're going to flip that sign. Moreover, let's do one further step, which is the following. So let's go back to the time order formula. Yes, this one, we wrote it in this form yesterday. Right? We wrote it as step function times commutator, sandwich between the states. But there is another identity. That you can use. Yesterday we saw you see now I'm expressing the time ordering in terms not of the step function that kills the past, but the step function that kills the future. Okay? That's because I'm going to use antiparticles. And this one, for the same argument I used yesterday, once I LSG reduce this, it's going to be is gone. So doesn't contribute by energy, by stability of the particle, doesn't contribute to the amplitude. Exactly for the same argument. Okay. So you can rephrase everything in terms of the commutator killing the future and inverting the sign of the energy. So that is going to give you. Let's go in the forward limit. So M2 bar going to M2 bar. The forward limit is given by the integral dx e to the minus k dot x. Step. So notice there's a minus sign. So let me. In fact, I haven't been careful. Yeah, I wrote equal. Actually, there is a prefactor. There's a. Yeah, so there's an, yeah, okay, maybe it's not too important, but the important point is that there is a minus sign relative there. There's also a normalization factor, but it's not too important. So I'm not gonna keep track of it. Is I times a positive now. Okay. But for the purpose of the argument, it's actually slightly better to define a new function. Let me define m bar of k, which is the same, but with opposite. I want to still do a Fourier transform, the same definition. So I'm going to flip the sign of this. Okay, so sorry. Here, yeah, thank you. No, I'm not flipping the sign. No, sorry, I'm not flipping the sign. I'm defining a new function, which is m of minus is this function for minus k. Flip the sign of k. So, in which region can I extend this function? Which values of complex k this function is analytic, in your opinion? The lower plane, right? Because this still vanish on special separation, but now the step function is killing the future. So the support is at negative u, negative v, so you can extend in the opposite direction, precisely. So this is telling you that m bar of k is analytic for imaginary of k negative. Moreover, by the definition, it corresponds to the cross product when I go on the real axis, but on the negative side, basically. Okay, so I have two functions at this moment. So I have so this is the S-plane, complex S-plane. So I have I'm analytic here, and when I approach the real axis from above, physical S, I'm getting the 1-2 process. I'm saying when I go, I approaching the real axis from below for m bar. I'm approaching m12 bar for negative k, so which is going to be this region here, basically minus s, approaching this region here. And the point is that, so at this point I have two functions that in principle have nothing to do with each other. So one function is defined here, another function is defined here. It's kind of cheating writing on the same plane, there are two functions of different domains. In fact, they have the same function. I can analytically continue this one to this one, and because they agree on the common boundary. So this is this important theorem in complex analysis. When you have two functions analytic in a region and they agree on a common boundary, they are the same function, which is analytic everywhere. So why is the case? Because you can take the difference you see, so because this minus sign here, you have one with a step function, and the other one with the step, well, the opposite step function, so you're going to get the Fourier transform of the commutator without step functions. And this is going to vanish here, below threshold. So let's see why. So this one, for example, so these are the difference of two terms. So let's look at one of them. Both separately they vanish. So it's IKX, 1, JX, J dagger 0. So let's insert a complete set of states. Then I have minus swapping the two. And then I have a sum of the phase space of m bodies. So this one you use momentum conservations. So this one is nothing but J0 e to the minus Pn x plus e to the minus I Pn minus P1 x. The dependence on x is completely known here, right? So the integral in x, I can do it. Just exponentials, right? By momentum conservation. So this gives me a delta function, which is nothing that there's nothing momentum conservation. Okay, so the momenta of the intermediate particle has to sum up to the momentum you are injecting. Momentum due to P1 and the momentum that comes from the Fourier transform. Okay, just that, nothing deeper than that. It's going to give you a delta function, the integral in d4x. So this part here, the first one, is proportional to the sum over all states, 2 pi to the fourth, delta 4, k minus plus P1 minus Pn times the matrix element 1, J0 n, and then I have basically squared, I think, yes, squared, minus the other combination, for which you can play the same game. Now you see that if you go below threshold, so imagine you take, so K and P1, you choose it. You're doing the Fourier transform. You choose your K, and you choose your energy of particle 1. Okay? So let's choose it. Let's choose them. So let's choose K0 plus P10 to be below the mass of the lightest particle. So let's call this lightest. Lightest particle. But then this delta function has no support. 0. So in this region, which is below threshold, when this arises, these two functions agree, and therefore there's a single function, which is analytic everywhere, that gives you the amplitude when approaching this axis above threshold. Above threshold, they are not necessarily equal. By the way, this argument shows you that this in general is not going to be 0 when you're above threshold. So here, there's probably a branch cut. It depends on the theory. Depending on the free theory, no branch cut. Interacting theory, branch cut. Weakly interacting theory with exchange of single poles, it's going to be poles. So what's happening here is model dependent. But below threshold, nothing's happening, so the two functions are the same. Above, you get 1, 2 going to 1, 2. Below, you get 1, 2 bar going to 1, 2 bar. The cross product. Okay? So this is nothing, this is basically a proof of cross symmetry. Okay? So there is a path, you can analytically continue from this place, and get the antiparticle amplitude. This is the simplest possible proof in the simplest possible set. Okay? So this is the proof away from forward with spin in general is a mess. So that's why I presented this. This is very simple. Maybe it's not very simple, but it's as simple as I was able to imagine. There's a further comment I want to make, that what if you approach the region here above threshold for the cross product, but on the wrong side? What is going to give you here? You know? The complex conjugate. So is there? So I reverted the epsilon here, so it's gonna. Okay, let me maybe write it better. Maybe write it better here. M of S star. So the reflected is just the complex conjugate of S. Okay. It's also important. The way to prove it, well, in this case, you don't need to prove it because we have just explicitly the function here, here. You can just check it. Okay, you can just check it. Take it, this function, this property, apply it here. You know the function below, you know the function above. You check it, and indeed it is the case. Or if we did not extend it below, another way to get the same result was we establish analyticity above. There is a technique to extend it in a lower region. This is called the Schwarz reflection principle, which is through complex conjugation. And then when the function is real below in the real boundary, then is a single function everywhere which has this property. I didn't want to do it this way because you need to know this theorem. Instead, this derivation, you don't need any theorem. Okay. Which follows from yet another theorem, a famous theorem in complex analysis, that function is analytic when you can take path for any, so analytic in any open set when any path within that gives you 0 when you integrate along any contour. And you can do, if analytic here and here, you can do just a contour like this. Then you do a contour like this. Right? These two cancel because you are below threshold. And so you're analytic everywhere up and down. This is schematically how the proof goes. Questions? So this was this mathematical step that we needed to establish analyticity. This is analyticity, maybe a few comments. Yeah, so I was about to say, outside from the forward limit, there are various things that are being established. So one is that you are analytic for negative t, so meaning physical momentum exchange, negative t, you're also analytic, but within a limit. So t can be negative, but not too negative. Typically, what has been rigorously proven from axiomatic quantum field theory by people in the 60s, some order 100 times the mass of the particle, something like this. Okay, depending on the flavor of the particle, depending on the properties of the particle you're scattering. This number can change a little bit. It can be 50, it can be 120. Okay, it's not too important. There is a conjecture, larger regional. So we are talking about analyticity in S. Okay, so we are talking about analyticity in the fixed T, analyticity in S. So for fixed T in this range, you're analytic in S, exactly in the same region I was showing you. Negative for this conjecture that for negative T as large as much larger than this, like minus S with S, the region where you are here in the plane, you are also analytic. This is at least for the lightest particle. It's called maximal analyticity. Never proven, never disproven. Up to I don't know how many loops checked. And so on. This is some of the results. Another set of results is the following: that for any S, and for any T, you can show that you're analytic not in the whole complex plane except the real axis. You can show that you're analytic for any T. Negative, you can show that you're analytic outside a region like this, that scales with T cube. Is another result from people in the 60s. So when T goes to 0, it shrinks, you're analytic everywhere. And if T is large, you have to go to very large S. In a sense, you need to be forward relative to T, right? So S is very large, basically you are forward, right? Because T over S, which is the scattering angle, is going to be small. Okay? So that's the intuition why this is true. And this is also true with particles with spin, massless, except, well, okay, there are various caveats. For example, this shrinks. So for massless particle, the branch cut, there's no, this argument I was using, you have an amplitude analytic here, analytic there, and on the common boundary, they agree, I can no longer use it, okay? So I need to find another path of continuation. That's what, there's a famous paper from Bros, Epstein, and Glaser, where they show that there's always a path when you can do it. If you want to challenge yourself, reproduce this paper. I wasn't able, so I tried hard, and I think it's very hard. Yeah, so I think the reason is the following. Why is it hard? Because you need to know complex analysis for several variables, which is completely different than complex analysis for a single variable. Completely different. So it's not like a stupid step from for real analysis when you go from one variable to two variables. It's basically the same thing. So no, there's a notion of envelope holomorphicity, which is very important in this story to extend the regionality. They use it all the time, and so it's certainly not subject of this school. So we assume for granted what I've shown here today. So keeping in mind that much more has been established. Okay, we will work in a reduced with using much less than what we could use. Okay, but keep in mind that you can derive much more. Okay. Questions? So now let's put this to work for something good. And for that, we will need another ingredient, another one that's very fundamental at the core of quantum mechanics, which is unitarity. So we assume now the following. So analyticity, we assume it, or just check it. Then we will assume unitarity, meaning in particular, I mean, this implies many things. One in particular is the optical theorem. Maybe not in this form. Maybe write in this other form. That M. Let me write this way. Discontinuity of the amplitude 1, 2, going to 1, 2, plus epsilon. So which is defined as the amplitude from above minus the same amplitude. I mean, it's true for any label here. I could drop the label. Okay? It doesn't matter. So the same is going to be true for the other channel. So the difference between approaching the amplitude from above minus the amplitude approaching it from below, divided by I, because here divided by I, is equal to 1, 2, m, 1, 2, which is in particular is a square. In particular is positive. Okay? This is nothing but the optical theorem because, because of the other property we established before, which was that if you have an amplitude, you take the star, you're gonna get this. So this was nothing but m minus m star divided by I. So it's just twice the imaginary part. So the imaginary part is positive. Therefore, okay. And the last step that we will need is the following: that the amplitude can grow at infinity, but not faster than s squared. Okay. I think you in the first week. By the way, you haven't seen the analytic proof I presented in the first week, or did you? Sorry? Not in this form, okay, so good, at least. I'm not repeating too much. This one, if you have a theorem with gap, is actually implied by a theorem, which is called the Frossard-Brown. Frossard, or I would add Martin. Frossard had a very good argument, and Martin made it a proof that the amplitude goes at most in a gap theory, goes at most like s log square of s. So in particular, less than s squared. Okay, we will need less than this, so we need this, and a fixed t, by the way. So this is fixed t. In our case, 0, fixed. And so this is true for t equals 0. In particular, the only exception I'm aware of is in gravity, where indeed is gapless, so this doesn't apply. And in that case, however, what has been shown recently, like a year ago, is the following. With gravity, if you work with a finite t negative, you take s very large, this one also grows less than s squared. This has been shown by Zhibuedov and his student Herring, Kilian Herring. And the idea is beautiful. So I recommend to read it. Maybe I can give you, maybe the sketch is the following. So fixed T, large S. So the scattering angle is going to 0. This is going to 0. And the energy is becoming large. So you put yourself in a condition. You scatter little, but the energy as large as you want in gravity. That's what is called trans-Planckian eikonal scattering. So it's precisely what happens when we scatter, I don't know, like a planet against a black hole. Both have mass gigantic relative to Planck. That's trans-Planckian scattering. You can still manage to do it because they are very far, very separated. The deflection is very little. The scattering angle is very small. We know since Newton how to do this calculation. Okay? So they were able to establish this 0 thanks basically to Newton. So this is enough, is almost enough to know Newtonian dynamics to establish this. Okay? Not quite. I'm exaggerating, but so this is basically comes from using eikonal trans-Planckian scatter, which is a regime you can control. Because gravity becomes stronger with energy, yes, but it decays with distance. So to having a small angle, when energy becomes large, you need to go to long distance, such they deflect very little. And so being long distance wins, so it allows you to do a calculation. Okay? That's the way the proof goes. Okay. So with this ingredient, let's establish some positivity. In the simplest case, scattering of pions, of one flavored pion, so one Goldstone boson from you want spontaneously broken symmetry. So let's write the amplitude in infrared for that theory, unless there are questions before on the assumptions. So in the forward limit, the one we have been working, this gives us C2 over M4 S square. This one vanish. That one gives us C4 M8 S to the fourth, and so on. Only even power. Do you know why even power? Why there's no odd power? Well, we are scattering a neutral, one flavor Goldstone boson, a neutral particle. So crossing, in this case SU crossing. So S to U, U is so is minus S minus T, but T is 0. So S to minus S, and since the particles are neutral, the amplitude goes in itself. So it must be even. It must be even in the argument, in this limit, the forward limit. Okay, so let's use now analyticity. We know that the amplitude, let's draw it here, in the complex as plane, is analytic here, is analytic here. In this case, this one may be closed, but let's open it maybe with a little mass, close it at the end. The scalar is not a big deal, adding a mass. And let's consider, I want to have a way to select these coefficients through a dispersive argument. So, for example, I want to select this one, say, I want to select this one, I can just take a contour around the origin of the following. Yes, over S of M, so I divide by S squared. I want to select S squared, so I divide by S squared. Then I take a contour around with this ds over S, then divide by 2 pi I. Cauchy theorem is telling me that so this has a simple pole at the origin, so this is going to give me C2. This we are using analytics. We are using the first, using this. So we are doing a contour around the origin. There's a pole here we inserted, so we divide it by 2. Then we inserted the pole. This is going to give us C2 over m to the 4. What about, for example, C4? C4 over m to the 8. What is it going to be? Yeah, exactly. So now I divide by s to the 4th. I integrate ds over s around the origin. Right? This picks this residue here. So we get C4 over m to the 8. So all of these terms can be picked in this way. So Cn, C2n over m to the 4n is going to be integral pi I ms over s to the to n ds over s. Okay? So this analyticity, we can calculate this Wilson coefficient just by doing some integral in the infrared. Okay? Now, because analyticity, the same integral doesn't matter, so you can do another contour. All right, you can do this contour, you get the same answer. Right? So this is a stupid contour, doesn't help you. So the contour that helps you is this one. And Why helps you? Well, because this branch here, standing bigger, 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 is going to be killed by this condition. Right? Because I'm dividing the amplitude by a lot. So this one doesn't grow with distance. I'm dividing ms by s with a lot of powers. Right? So I can drop this contribution. So all these C to n here are equal to the integral of the big circle at infinity, which is 0. Well, as long as I'm taking n, so in this case, I'm taking it larger than 1. Okay, so this I can drop it for n, so subject to n larger or equal than 1, plus the contribution from this part and this part. So there are two integrals. So one starts from the, what do they call it? Yeah, call it m infinity ds prime, s, then plus the integral ds over s plus integral from minus infinity to minus m square ds over s of the discontinuity, right? So the amplitude above minus the amplitude below, which is a sum of squares. So this one is equal to ms plus I epsilon minus m s minus I epsilon divided by 2I, right? So basically, little contour equal that's what the one integral is the first, this one is the second. Now you change variable here to put in the same form as this one. So you send s to minus s. This one doesn't change. You have to change the orientation, pick a minus sign. Here you get a minus s. Here a minus s. So this one I use further condition, which is this one. Land in, so there's a pi missing, this pi here. So you get these two integrals sum up together, so give you twice over pi, integral from m square infinity, ds over s, the discontinuity, ms plus epsilon divided by 2I, and that by the unitarity is positive. So we just established that each term here, each of these terms, crucially, is because I was able to drop the contribution at infinity. Because I restricted to take what are called technically subtraction, even though, I mean, division would be better name. And that's okay because I'm starting with already with S squared. So if I divide by S squared, thanks to this condition, I'm able to set a bound. Suppose I wanted to discuss a theory which had also the constant term. I would not be able to bound it, right? Because then I would need n equals 0 here. And this one wouldn't decay fast enough at infinity. Okay? Very important. You're able to bound something which is sufficiently irrelevant. Okay? The marginal and the leading irrelevant, typically you are not able to bound. For example, the dimension 6 operator, typically you are not able to bound. In this way. Okay? Perhaps there's another way, perhaps. Okay? This one. So I thought this you have seen this in the like this. I mean, you can demand that, but there are theories that violate this. So QCD, which is a theory of mass gap, satisfies the assumption for Martin. In fact, it grows. You saturate pretty much the bound. It goes like S over square S. In fact, there is a mass of the pion here in QCD. Okay. And you will not get 0. You will get divergent, infinity. So you will get, you will not be able to bound, for example, the coefficient of the leading coefficient in carrier Lagrangian, which grows like E squared. You're not able to bound for this reason. This follow, I think, I don't remember if I put it in the notes or not. No, maybe I didn't put it. There is a nice sketch argument for why this is a consequence of locality, so maybe I should stress it. So this comes from a notion of locality. So that's where locality comes into play. That is what we were somehow similar to the argument by Giboet and Herring. So you're going to fix T large S, the scattering angle is small, you're dominated by the lightest particle exchange in T channel, that you require that if it's massive, past a certain mass, it doesn't longer contribute. There's a range of interaction set by the mass, and after that it decays exponentially, your partial wave expansion is cut at that scale. You have an estimate where to truncate the partial wave expansion. You use unitarity for a certain region and this estimate by locality for another region, put things together, scramble, and you land in the Frossard-Martin model. Okay, but the technique, yeah. I think you have seen something along the line in the previous week. How much time I have? Oh, sorry, questions? Sorry, what did you say? I missed the first part. Equals 0, yes? Yes. So I didn't put the mass. I'm taking the mass limit for simplicity, simplify. You can still, rather than work in the S-plane, you can work, for example, even at finite T, you can work in the S-plane shifted a little bit around the crossing symmetric point, because in itself, your circle would still swap to itself by crossing symmetry. It's not a big deal. Okay? It just simplifies the form. So how much time I have? Do I have 5 minutes? No, but I think it would be good if I say something more about loops now. Can I have it 5 minutes now? Because later I want to change a bit, want to introduce some new concepts. So notice here I was using a 3-level Lagrangian, right? And indeed, by consistency, in the infrared, I didn't write the branch cut going all the way to the infrared. So I started the branch cut from the cutoff of the theory, consistently with the assumption I'm doing. I'm making assumption in the weakly, in the UV, in the IR, the theory is weakly coupled. I neglect the effects of the loop in the infrared. Okay? I'm taking into account instead whatever, even strongly coupled theory in the UV. Okay? So how well is this assumption justified? Okay? I think this is something that everybody gets it wrong. So we wrote a paper that nobody understood about it. So I think I want to say it clearly. So, let me do an example. So let's add now, let's include loop corrections here. So our ansatz is not this, it's a little bit different. So let's write the new ansatz. And one loop. Let's write the leading effect. So we're going to get from C2, for example, two insertions of C2. The lowest dimensional, looping the lowest dimensional is the most important effect, okay, you can possibly have. So let's look at the leading effect. So C2, so over n to the fourth s squared. This guy doesn't get normalized because it's the lowest dimensional, but it normalizes as s to the fourth. So two insertions gives you m to the 8, so you get some number, C2 squared, log s running scale plus now C mu gets normalized, so C4, so running 16 pi square and the 8 and so on. Okay. So the story changed a little bit here. You have some branch cut in infrared. Or maybe let's use another color. There's some running, some discontinuity from the light guys. But in this case, it's this diagram. Okay, C2 is a discontinuity due to this diagram. Okay? We cut it. The imaginary part is not zero. Okay? It contributes. So, in order to account for this, rather than working, you could work. Okay, you can just repeat everything, just shrinking below the threshold of this guy, but it would be a disaster from the point of view of infrared divergence. It's not a good idea. So what is better is actually, and also makes more sense, is to keep the same radius we had before, but consider a slightly different contour. Okay, so we're going to do what we call arcs. Which are a function of a radius of a so is this integral? Is the integral? I mean, maybe be careful. So 1 over 2 pi I integration on a particular contour, which I'm going to draw now. D s prime over s prime of the amplitude divided by, in this case, let's look at arc 2 for simplicity. So divided by s prime square. S prime is this, where the contour is the following. So there is a branch cut in infrared that goes to some infrared scale, all the way here to m, the UV scale, and we do some integration in between, okay, something like this. And we stop, then we go again. Okay. So if we neglect the infrared loop, it's just the same calculation done before. Now there's a little bit of a difference. How much of a difference? Well, it's just you can add this term. So the difference is the integration of the discontinuity in the infrared. Okay. So this contour will pick just the pole we have here. So the difference is just this integration in the infrared. Okay. In particular, since it's positive, the discontinuity is positive because of unitarity. It means that the arc is monotonic with the radius. Okay, it's a function of the radius, s now I'm taking. So that's why I call it the integration variable, the dummy variable s prime now. Before it wasn't a function of s because there was no discontinuity. You can do before the contour, doesn't matter. Now it matters because you have an infrared contribution. Contribution is minimal at larger s, monotonically decreasing. And because this branch gives a positive contribution because of unitarity. Therefore, if you establish positivity at the largest possible S compatible with the effective theory, that's good. You don't need to do anything else, because if you decrease the arc, since it's getting larger, it's going to be positive automatically by unitarity. So the only thing you have to establish are positivity properties at the largest possible S compatible with the effective theory. If the effective theory is weakly coupled, S is going to be O order M squared. You can push it. It's a small coupling. You decide which accuracy you want to achieve. Depending on how much accuracy you want to achieve, you stop at some point. Okay? So S is going to be not that far from M squared. Okay, with this in mind, let's calculate the arc with these new ansatz, with the loop. So this is going to be the arc. This one is going to pick just C2 over M squared. M to the fourth, sorry. Then I have to do the integral of the discontinuity. I'm just saying, this arc, you can even use this picture to do the calculation. Rather than do this integral in the complex plane like this, you do it here, pick C4, and then you add the integral along the discontinuity, okay? Which you know, because you know the infrared by assumption, you know the effective theory. What is the discontinuity of a log? What is the discontinuity of a log? But first of all, is continuous, discontinuous? Is analytic the log? Is analytic? No, right? The log of minus 1 plus I epsilon and minus 1 plus I epsilon differed by pi, right? The pi. Okay, so it's a constant. It's the simplest possible. It's just a constant. So this integral of the discontinuity here just is going to give you C2 a number, which, by the way, you can say the sign of this number by unitarity, right? Because we said that this integral we are going to do can always push you in a certain direction by varying S. So the sign of this guy is fixed. Nothing can change it. Okay? It's going to be minus 7 over 10. Okay? Order one number negative, consistent with the fact that it has to go in a certain direction. So you get C2 square 16 pi square, m to the 8. Then you get the pi from the discontinuity of the log. Here is missing s to the fourth, nobody said anything. Then s to the fourth. Then I'm dividing by s prime to the fourth, then divided by s prime square, d s prime over s prime. Integrated from some higher scale to some other scale s, the radius of the arc. Okay, so this one is 1 over s, give you s prime square. So this one is gonna give me C2 m to the fourth multiplies 1 plus crucially there is a 1 over pi here from the definition. This pi here we're gonna cancel with this pi. So plus C2, some number here, 16 pi square log s. And no, sorry, log is gone. So C2 16 pi square s square divided m to the fourth. Yes, plus these corrections. Yeah, you see there's a s square here, integrating ds over s. So give me this evaluated at s. So s prime evaluated at s. So it gives me s square. So within the validity of effective theory, C2, this term is never going to beat 1 within the effective theory. Okay? So C2 positive, established. There's no problem. So for the arc 2, no problem. For the arc 4, so let's go to the next. Yeah, I thought it was much faster, sorry. So just telling you the result. So you repeat exactly the same calculation. You're going to get C2 square 16 pi square log S. You can even put the mu. And that you can actually use this equation as a, since these are integral of amplitude, which are physical, you can take an RG equation. You can say, this is a bonus comment. D mu of the arc equals 0. You get the RG equation for this guy. It's going to give you the beta function of this guy is this number. And, but that's not the point here. The point is that you're going to get that basically running C4 is positive. Nice, okay, what we would have naively expected. Okay, you do loops, coupling run, running C4 positive. But now the story changes from 6 onward. So let me write the generic one. Okay, maybe 6 m to the 12 a6 of s. It's gonna go by dimensional analysis basically. Because you see, A6 is associated to a very relevant operator. You're going to pick C6. You're going to try and write it in terms of C2, which wasn't that irrelevant. So you need to make the dimensions right, you need powers of S in the denominator. So you see that the information about C6 is completely swamped, polynomially so, by the less irrelevant operator. So it's not running. This was running, only logarithmic change. This is a polynomial change. So you don't learn much about C6, okay, in this case. Things get worse. It's basically why we call eigendimensional operator irrelevant. Why are they irrelevant? Because to the calculation, what matters are the less irrelevant. Here you see it. I'm calculating an observable. C6 doesn't matter. It's dominated by this guy, okay? And so the generic, and finish with this comment, is this one. So m to n an of s is going to give you Cn plus C2 square 16 pi square m to the 2n minus 4 divided by s to the n minus 2. So if I demand, I have a chance that this is subleading to this if I take S sufficiently large or C2 sufficiently small. Okay? Perhaps I can win. I can still be in business if C2 sufficiently small or S sufficiently large. That this. So let's impose this. I require this one bigger than this. So this gives me a condition. It gives me that C2 squared over 16 pi squared, my loop factor, must be small enough then S over m squared to the powers n minus 2. Yeah. This might be true for the first few terms in the effective theory, but it cannot be true arbitrarily so. So you fix your theory. You measure this, for example. This is a small number, you can do loops. Good. Can it be smaller than this for any n? No, because S is smaller than m squared in the effective theory. This is smaller than 1, so there's an n sufficiently large that is going to be smaller than this one. You violate it. You're going to be dominated. So doesn't matter how small your coupling is, the result is going to be swamped by the loops. Okay. So we are going to, for example, we established infinitely many positivity conditions. Now, before we said all these C's are all positive. Should we really claim infinitely many positivity conditions? No, only a finite number. This now, finite number for which you can claim positivity. So this is the fact. Or loops. Questions? Yeah, I didn't say anything about this. Does the vanish in the forward limit? If there is, the plan would be to try to say something in the next hour. And not only, I didn't say, for example, with the causality, we were showing that C2 has to be larger than C3, and in fact, C3 has to be larger than C4, and so on and so forth. This I didn't show you. I'm going to show you in the next hour. Unless we keep going now, straight, without pause. No, maybe it's better. I think from the face, I think it's better to have a pause. Sorry that I went over significantly. But I think it's an important point. I think everybody missed this somehow. Even Nima claims infinitely many positivity condition. No, sorry. Of course, you can always marginalize over your coupling. You can say, ah, but I want to access an even larger number, I decrease my coupling. You're cheating because your coupling, you measure it, it's not a free parameter.